Okay, so in the last couple of videos, we saw that we could compute the GCD of a and b, two positive integers a and b, by noticing that the GCD of a and b was equal to the GCD of a and b plus k times a, where k is any integer. And we proved this in the last video, and then the strategy was to look at whichever one of these is bigger, and then subtract the largest multiple. So taking k as like a negative integer, subtract the largest multiple of the smaller one that you could from the larger one, and we reduce it and we repeat until we get the GCD. And you might have been kind of annoyed when you saw this because it was a pretty quick, simple procedure for doing that. But in most number theory classes, they teach you the Euclidean algorithm, the full Euclidean algorithm. This is a very similar thing. And so you might be like, why did they teach me this big long thing when I could have just used this? And so first of all, I am of the opinion that this should be taught more. Of course, that's why I'm teaching it. But the Euclidean algorithm, so the one that you might have seen, where we start with a is equal to b times q plus r, the remainder r. This is q is the quotient, and then r is the remainder. This one has its uses. What is the use? What is the primary thing that we can do with this that we can't do with this one? So why we're going to learn about this one in this video, despite the fact that they might actually just test you straight up on this. I don't want you to do this Euclidean algorithm version, or the official Euclidean algorithm on a test. The reason that we like this one is because this can be used to find modular inverses, which is a pretty big thing in number theory. We do this in number theory courses and courses that have like a number theory component and contests all over the place. So finding modular inverses is a big deal. We're going to learn how to do it. Okay, so what's going on with this? Why do they do this? We start out with this a and b in the positive integers. It doesn't have to be positive integers, but it's simplest to do it when they are positive integers, and in most of the applications that we're going to be doing, most of the problems is going to be positive integers. So we'll take, and suppose a is bigger than b, so without loss of generality, as we say a is bigger than b, well, we can write a is equal to b times q plus r. For r and q are in the integers, and importantly, 0 is less than or equal to r, which is less than or equal to b. And this actually, the fact that we can do this is a theorem of its own. This is the division algorithm. You can actually prove this. It comes from, I think, the well-ordering principle. It's one of those really sort of fundamental, obvious things that you actually do have to prove. But just as an example, if you have, say, a is equal to 7, and say b is equal to 2, then we can write 7 is equal to 2 times 3 plus 1. So here we would have the quotient is equal to 3, the b is equal to 2, the r is equal to 1, and then the a is equal to 7. And generally, I think this is a better way to sort of understand things when they're in this category where they're pretty obvious and it seems like they shouldn't need to be proved, but they actually do. Usually, the proofs can be pretty hard to wrap your brain around, especially when you're just starting out. But something like this makes it sort of clear what's going on here. It sort of elucidates it. You look at the largest multiple of b, the 2 that you can get, which is less than the 7, the a, and then you add the remainder, what's left over, 2. So you get 3 multiples of 2, it's 6. If you add another one, then you're going to go over 7, it's going to be 8, so you add 1 as the remainder. And there's no restrictions on q, right? Here, q is bigger than b, right? The 3 is bigger than 2, but the 1, the r, that has to be less than 2. Why? Well, if 1 was bigger than 2, if the remainder was bigger than 2, if this was like, I don't know, say 3, then we could split up the 3 into a 2 and 1, and then instead of 2 times 3, this would be 2 times 3 plus 2. You'd factor out 2 would be 2 times 4. You would increment the quotient, right? If the remainder was bigger than b, then the divisor, the thing that so this is actually a division statement. We're dividing a by b with remainder. If the remainder was bigger than the divisor, then you would just increase the quotient, right? So the remainder is always in here. And this is the crucial thing. Because what we're going to do here, the beginning of the Euclidean algorithm is going to be the observation. We're going to say observe that the GCD of A and B, which is what we're trying to find, is actually the GCD of B and R. And this is why I was saying there's sort of a relationship between this and the proof, actually, of the sort of faster algorithm, the faster kind of version of this, because they're based on the same principle that we did in the last video, is that the way that we prove this is exactly the way that we prove this thing. These are actually the same, basically the same idea here. Any divisor of A and B, if you have D as a divisor of A and B, well, you can factor out a D from A, it's D times K, and you can factor it out from B, it's D times, I don't know, M. You can factor it out from both of these, and then subtract it off, and you'll show that that divides R. So all of the common divisors of A and B will also be common divisors of R, and therefore will be divisors of R, and therefore common divisors of B and R. And it works the other way as well. If you have a common divisor of B and R, it will automatically divide A. You can factor it out on this side, and then it will be a common divisor of A and B as well. So since the common divisors of A and B are the same as the common divisors of B and R, the greatest of all of these, the largest element of this set of divisors, will be the same as the largest element of that set, because just like in the proof of the little sort of theorem behind the faster algorithm, they are the same set of divisors. So this is this is the motivation behind the Euclidean algorithm. The reason that it works is that we can reduce the problem finding the GCD of A and B to finding the GCD of B and R. And R is smaller than B, right? B was smaller than A. So now we're reducing the size of the numbers that we're working with. We're trying to find the GCD of B and now a smaller number. And we're going to keep doing this and reducing the size of the numbers that we're trying to find the GCD of until we run out of space. This is the well-ordering principle of the positive integers. The positive integers are a well-ordered set, which means that any non-empty subset has a least element. And so that means that, which is 1. So the point is that we keep going down and down and down, reducing the size of these numbers, and this has to stop at some point. And we will get the GCD of two smaller numbers somewhere down here is the same as the GCD of A and B, and whatever that GCD is down here, that's our solution. That's our GCD of A and B. And the idea is the process has to terminate at some point because of the well-ordering principle. Okay, so we started out with wanting the GCD of A and B. We know it's the same as the GCD of B and R because we did this setup here. So what are we going to do in the next step? We're going to do the exact same thing. If we want to find the GCD of B and R, we're going to write B is equal to R times now some other quotient. We'll call this Q1 and plus R1. So what have we done here? We've done the same kind of thing that we were doing with the exact same thing we were doing with A and B, but we moved this R here because what's happening here? This equation, just like this one, told me that the GCD of A and B is the GCD of B and R. This one is telling me that the GCD of B and R here, the GCD of B and R, is going to be the GCD of R and R1. And by the exact same reasoning, any common divisor of R and R1 is going to be a common divisor of B and R, and vice versa. Common divisors of B and R will be common divisors of R and R1. Exact same argument. And this is the crucial thing, 0 is less than or equal to R1, which is less than R. The same way that R had to be less than B here, R1 has to be less than R here, strictly less than R. And we just keep going like this, right? And we get, so the next thing is we're going to get R is equal to R1 times Q2 plus R2. And this is where it starts to get confusing, right? People's eyes kind of glaze over in class because of this, because now we're throwing in indices and it starts to sort of lose meaning. The idea is that each time we're moving the R's down here and getting the GCD of R1 and R is now the same as GCD of R1 and R2. And then we're going to move, we get the R1 is equal to R2 times Q3 plus R3, and the GCD at this point, I didn't write the last one, maybe I should just put it in for this one. For both of them, at this stage, we get at this stage, we get GCD of R and R1 is equal to the GCD of R1 and R2. And 0 is less than or equal to R2, which is less than R1. So the remainders we're working with are getting smaller and smaller. They're strictly smaller. And they're always bigger than or equal to 0. So this can't go on forever, right? We're going to have, and then we do these dot, dot, dots. We get Rn is equal to Rn plus 1 times Qn plus 2 plus Rn plus 2. And this is just writing the general term, where we see that the subscript of this R is 1 more than that R, and then the Q and the other R out here, the remainder R, those have the same one, which is 2 more than that one and 1 more than this one. So just getting the general term. And we keep doing this until we wind up with R, let's say, I don't know, K is equal to Rk plus 1 times Qk plus 2 plus R, actually, you know what, why don't I just do this? We'll make this the second last one. I was going to make this a bit more complicated than it needed to be. Rn plus 1, so moving this one down here, is going to be Rn plus 2 times Qn plus 3, and then plus 0. So Rn plus 1 is, it has Rn plus 2 as a factor, and Qn plus 3 is the quotient. And so what does this tell me? This tells me that Rn plus 1 has Rn plus 2 as a factor, so Rn plus 2 is a divisor of Rn plus 1. So the GCD of Rn plus 1 and Rn plus 2 is Rn plus 2. Because it is a common divisor, and we can't have a common divisor of two numbers which is bigger than one of the numbers. So Rn plus 2 is the GCD. And in the Euclidean algorithm, they always tell you, go back and look at this one, right? This is the GCD. That's why. Because when we continued this process, right, the GCD of AB is equal to the GCD of the next pair of numbers in each one of these things. So this was GCD of R and R1 is equal to the GCD of R1 and R2. And we went all the way down to here at this stage, we had the GCD of A and B, which we started out looking for, is equal to, and actually that was up here. This all came down from this spot. It all ended up being equal to, at this stage, the GCD of, it's going to be Rn plus 1 and Rn plus 2. And we just figured out, because that's this one and that one, right? It's always the GCD of these two in the expression. So what is the point of this? Well, this turned out to be Rn plus 2, right? Rn plus 2 turned out to be the GCD of Rn plus 1 and Rn plus 2, which was the GCD of Rn and Rn plus 1, which is the GCD of Rn minus 1 and Rn, etc., all the way back up until it turns out to be the GCD of B and R, and therefore the GCD of A and B. So that is the Euclidean algorithm, and that is why it works. It just starts out with this fundamental observation that the GCD of A and B, once we do the integer division, divide A by B with remainder of A is bigger than B, that the GCD of A and B is the same as the GCD of B and R has to be strictly less than B, and you can only reduce the size of positive integers so many times until you get something which is as small as it can be. So they're bounded below by 1, right? Positive integers, the smallest one is 1. So you can't do this forever. You terminate and you get a GCD. So this is one of the great things about number theory, that you get this awesome sort of far-reaching. I'm not sure how far-reaching this is. Very, very useful result. A lot of them are far-reaching, and they come from really simple, beautiful ideas. This one is just kind of useful and cool, and comes from a pretty simple idea. So that's the proof. In the next the idea behind it. In the next video, we'll do an example, and then just to sort of solidify this, And then we will see how we can extend this. This was just the basic Euclidean algorithm. The next thing is going to be to find the extended Euclidean algorithm and use that to compute modular inverses. Because this one, you might be thinking, as I'm talking about this seemed like a lot of work, right? Would I do this every single time when I could just do this thing where I take the brackets, right? And we'll do one of them both ways, maybe in the next video, and see that, yeah, this is a little bit sort of quicker and easier, and it does get you the right result. But this one, we can extend the Euclidean algorithm, because this is not the Euclidean algorithm, it's something which is similar and based on the same kind of idea, but this is the Euclidean algorithm. This can be extended to a way to find modular inverses, which is what we're going to use it for many times when we're solving problems that involve doing just that. That's a big thing in number theory. So that's up in the next video.